Good morning. The check-in link won't open until 8 a.m. So you're about 5 minutes early. Although for some reason the timer is not working. That one's working. Why is this one not working? No problem. Testing, testing. Hello, Valerie. How are you today? I'm pretty good. And I got the computer, my new my new setup set up so that it's definitely working. So it's a good starting point in the morning with the new system. Although there are going to be a few changes that I plan on making to the how we do the office hours. Not how we do the lectures, because this works well for the lectures, but I don't think it works as well for the office hours. So um, this afternoon, I will upload the updated calendar with homework. There's no homework this week because it was holiday week, Monday, Tuesday holiday. Um, so homework will be next week. I'll readjust the points for each homework and get all of that set up and adjust the calendar and get rid of the quizzes. So, and then I will start grading the homeworks and also upload your question and answer grades over the course of today and tomorrow. So I just wanted to keep you guys abreast of what's going on. Good morning, Franklin. But anyway, I am changing how we're going to do the question and answer. What I am changing is the question and answers are going to use the town hall mode in Teams. So they will be more private. And they will also allow you to tune in with video or audio and ask questions. So turn on a microphone and ask questions. Um, so I wanted the office hours and the Q&A to be more open, where you're not limited to. I wanted it to be more local to Queens College, uh, so not quite as public as the YouTube stuff, especially since I'm on for 3 hours. And I also wanted it to be more available to you guys in order of being able to ask questions and so on and so forth. So I will use a whiteboard, but unlike the whiteboard that you're seeing right now, the whiteboard that I'll use for Q&A will be open so that anybody can type or write in it. So I do recommend that all of you download the whiteboard app so that you can type questions in it and write in it, because going forward with the Q&A and office hours, I'm just going to use a whiteboard. I'm going to share it in the town hall, and we can all chime in and ask and answer questions on it. So that's a change that I'm making. I'm just not comfortable with the 3 hours of YouTube. That's all. So that's more for me than for you guys, but it does allow you guys to use a microphone to ask and answer questions. So I did want to let you guys know this. Okay, so last time we had defined open, closed, and isolated. Oops. Set a 30-minute Pomodoro, maybe 35 minutes. So last time we had defined isolated, closed, and open systems. And this was related to whether heat or energy or matter could flow. And I had told you I was going to use this reflux apparatus as a very clear way of defining these three systems. Now, the only way a reflux apparatus could be isolated I'm just checking something. A reflux apparatus can never be isolated. So this never. So, the check-in link should be open for everybody. So for reflux, got to get colors set up. Okay. So now it's never isolated because I've got heat flowing in to the water. And I've got water flowing in and water flowing out of this distillation, which allows heat to flow out. Because that's the whole point of this water in and out, is to remove heat from the gas that bubbles up. And because of that, it can never be isolated because heat flows in and out, and there is no way to set the boundaries to prevent it. And it'd still be a reflux apparatus. Now, I could, um, so how could I set this where it would be isolated? It wouldn't technically be reflux, but how could I force it to be isolated? So I could seal, if I put a stopper here, I turned off the heat there, and I stopped the water. Then it would be isolated. Oh, and I also put it in an insulated, a secondary container with insulation. Think ice chest. I can't spell chest, but okay. Um, that would be technically isolated. Can't do anything with it, but it would be isolated. The only thing, technically speaking, that quote prevents it from being fully isolated is gravity. Um, but generally speaking, we kind of ignore gravity for the discussion of isolation. But if you are in physics, they're going to make a big deal out of that. That to truly be isolated, you also have to account for gravity. Chemistry, we don't worry about that. Okay, so then I'm going to flip back just a minute to go get the reflux apparatus again. So you can see that isolation is it's a rare state. Now, closed versus open is pretty easy to maintain when dealing with a reflux apparatus. So, closed, I will remind you, no matter flow, heat flow. Now, we're going to define our system in order to get a truly closed system. We're going to define the system as the yellow liquid. And the surroundings is everything else. Well, yellow liquid slash gas. When we do that, we have a truly closed system. Because what's going to happen is as I heat this, um, the yellow liquid is going to begin to evaporate. And I'm going to get gas that comes up, and it goes into this little narrow tube. But the water that's flowing in and out cools the gas down. It recondenses, and it falls back down as, so it recondenses on the side, and it drips back down as water, as liquid, whatever your solvent is. So in general, the and in fact, this is exactly why you use a reflux apparatus, is because when you're doing organic chemistry, a lot of times your systems need a they need to boil for a very long time, like overnight, 24, 48, 72 hours. And if you were to do that, like think about on your stove. If I set a pot of water on my stove and boiled it, the liquid's not going to stay in that pot for 72 hours. It's going to boil dry. We don't want that to happen in a chemical reaction. We want our solvent to stay with our system and to stay put. And so the whole point behind a reflux apparatus is in fact to allow no matter to flow. The liquid boils, it hits that column of cold air because the water is cooling the glass. It condenses back on that glass and it falls back down into the, that's called a round bottom flask. It falls back down into the round bottom flask, and that process just goes on and on and on. And that maintains the volume and the matter in the reaction vessel, but allows us to heat to as high as we can heat for that particular solvent. So this is a really good example of a closed system. But notice I had to very carefully define the system as the yellow liquid gas. But I also had to make sure that I didn't define the system as the whole reflux apparatus, because if I had defined the system as a whole reflux apparatus, it would not have been closed, because I do have water flowing in and water flowing out. But that is, in this definition, is not part of my system. I'm only defining my system as where the reactants are, not as the rest of the apparatus. And that's why I can call this a closed system. Now, okay, so in terms of closed system, this is just a really good example of how you need to um, be very, very, very careful in maintaining where the boundaries are. Now, for an open system, if I wanted to define the same thing as open, so I'll remind you that open is matter flow, and this will show you just how sensitive this is, and heat flow. All I have to do is define the system as the yellow liquid. If I only define the system as the yellow liquid, not the gas above it that's condensing and falling back down, but just the liquid, then the system is open, because I'm heating the system to boiling and the liquid is leaving because it's converting to gas and it's going up, but that's not part of my system. So again, this is where you have to be exceptionally careful. And I can't, I'm going through this and reiterating this because a lot of the mistakes that happen in the discussion of thermodynamics, thermochemistry, arise due to fluid barriers. So somebody defines their system as one thing, and then when they start talking about it, they inherently shift the barrier to something else without realizing they've done so, and then they hit a contradiction and they say, oh, well, thermodynamics laws are violated, but they aren't really, because they change system and surroundings without realizing that they've done so. So, and therefore they've gone from a closed system to an open system without realizing that they did so. So you do have to be exceptionally careful with the definition and how you are defining system versus surroundings. Now, several of you asked very good questions about this. exceptionally good questions. And I will go through and answer your very good questions today. Um, so, Teresa, you asked, what is the most intuitive way to distinguish an adiabatic boundary from a diathermal boundary? Uh, a very good way of doing that is, does it get hot on the outside? So think about Starbucks uh, coffee containers. Those coffee cups get with if they didn't put that little paper sleeve around those coffee cups, you couldn't hold that hot coffee. The coffee cup is not very adiabatic. It allows significant heat to flow out of the edge of the coffee cup, and that means it's really diathermal because you can't hold it without a paper sleeve, and that paper sleeve is just basically adding what? It's adding a slightly thicker barrier and hence making the area where your hand is slightly more adiabatic so that you can't feel heat to flow. But that's why Starbucks coffee gets cold fairly quickly in its standard coffee cup because the heat is flowing pretty much out of the cup pretty rapidly. Um, Generally, anything made of metal is going to suck as a adiabatic barrier. But if you have a piece, something made of metal that's thicker, and you know that in that thickness is either a vacuum or foam insulation, that makes an incredibly good adiabatic barrier. Your ice chests that you carry like to the beach and stuff that are just plastic. Plastic's not usually a good barrier, but they're thick and they've got foam in, and that foam is a good barrier. So what you're really looking for as an adiabatic barrier is a material that does not conduct heat. Generally speaking, metals conduct heat very well. Ionic salts don't tend to conduct heat fairly well. Some plastics conduct heat well, other plastics don't. Most plastics actually really don't conduct heat well, but a lot of that's also going to be dependent upon thickness. So that's an area of study in terms of deciding, can I read this? So, easily, your question about when analyzing a reflux setup, how do we clearly define the system? You define the system in words, but how you define the system is going to determine whether it's open or closed. So if you define the system as the liquid and gas reactants and solvent, then the system is closed. If you define the system as just the liquid reactants and solvent, then the system's is open. If you define the system as the entire apparatus, it has to be open because water flows in, water flows out to cool the reactants um, that form as a gas. So you can define the system however you choose. The issue is depending upon do you want it isolated, closed, or open, determines how you define the system. So, in other words, the equations that we're about to derive and talk about and work on, they rely on is the system open, closed, or isolated, and they change whether the system's open, closed, or isolated. So the You choose how you define the system, but you have to recognize that the thermodynamic equations that model that system may change depending upon how you define the system. And sometimes you really need to be aware of that. So, another example of this, it's a good example since we're talking about this and we're getting ready to talk about heat flow, is if you're like me and you're a big fan of racing, most of the drivers they have to wear a fire suit. Fire suit's a really good example of an adiabatic barrier. It's designed to prevent the heat from external fire from getting to the skin of the body. And different fire suits have different ratings. So the fire suits that the drivers have to wear, I think, protect them for like 5 minutes, but it could be 10 minutes. But if it prevents heat from getting in, it also prevents heat from getting out, which means these drivers are sitting in a suit that is preventing them from cooling their body off by sweating. Now, it does have some stuff built into it to help wick the sweat away that will do some cooling in terms of how the material inside the fire suit absorbs sweat. But for the most part, if you can't get heat in, you can't get heat out. So a lot of drivers wear what's called a cool shirt. So the cool shirt is a shirt that has tubing that runs through it, very fine tubing, and they flow water into that cool shirt that then flows out. And that water that flows in is when it goes into its little compressor box, there's ice in that compressor box. That ice cools the water that's flowing through their suit. It melts over time, so during pit stops, the crew's constantly giving them bags of ice to drop in the cooler while they're waiting on gas and tires. It's a very odd way to do this, but that's how they cool their bodies down because the fire suit doesn't allow for that exchange of heat. Now, for that particular system, unlike the reflux apparatus where water in, water out, you really have to, if you're going to accurately model how that cooling works, you have to account for the water in, water out, because that's what's providing the cooling. And if you wanted to try to calculate to maybe come up with a new design that was more efficient or less prone to errors, your system, that water that's doing the cooling is part of your system, as is the human body, as is the fire suit surrounding the shirt and the human body. So you would have to account for all of that if you were trying to model or design for a new cooling method of cooling for the driver. So in other words, I know what you're wanting. You're wanting, I want a fixed barrier because I need to know what I'm doing. And the truth is there isn't one. Sorry. So it's an issue, and it's just something that you have to be. It's what makes thermodynamics hard. You have to be exceptionally careful and read questions carefully and really think about it. Sometimes maybe draw the picture to get a good sense of what you're modeling, but you need to be exceptionally aware of where the barriers are and what you're defining as system and surroundings. I know that probably did not make you feel any better, but that's the nature of thermodynamics. Teresa also asked, if the system is permeable and matter can enter or leave, how do we account for the energy change caused by matter moving across the barrier, and how is that different from heat? Generally speaking, if matter's moving across the barrier, it could be heat. It could also be a change in potential energy. So intermolecular interactions, which would be a change in entropy. Um, so yes, you do. There is an interchange. There is definitely energy change, but that's really going to depend upon the type of matter, the type of barrier, and a whole bunch of other stuff. So that question's really complicated, Teresa. And the other question she asked that's a really good question, especially at this point, is what is the difference between heat and temperature in thermodynamics, and why can two objects at the same temperature still exchange energy in certain situations like phase changes? Now, there you're really so what she's asking there is where I'm putting heat into a system, but the temperature's not changing, but the phase is changing. So where's the energy going? I'm putting energy in, but where's the energy going? And that is entropy. That's where the energy's going. So you can kind of view temperature as a measure of kinetic energy and entropy as a measure of potential energy. Now, that's not always true, but that kind of idea, especially when in chemistry, when thinking about chemical systems, that's actually a pretty good way of viewing things. And it even works in physics, although physics doesn't generally think about this. But when you rub your hands together, they get warm. Why? Why do they get warm when I rub my hands together? Well, physics will tell you that's friction. But what is friction? Um, from a microscopic standpoint, friction is the intermolecular interactions of the molecules of my skin with the molecules of the skin of the other palm. And those intermolecular interactions, as I break them and make them as I rub my palms together, generates heat. But that's a intermolecular interaction. That's a potential energy interaction that I'm changing. Now, that friction's also, this is why the temperature goes up on my palms. That friction's also changing the kinetic energy of the gas between my hands and also the gas in the little ridges of my skin, and that generates the increase in temperature. So that was a good question. Now, the question about spontaneous, that we will get to in the next chapter. We're not there yet. We're just talking about heat and work right now. We're not talking about entropy per se yet. So we will get to that question. Um, somebody else asked about microstates versus macrostates. That's an entropy question. We'll get to that as well. And also the interconnection between entropy and enthalpy. We'll get to that today, actually. But just in terms of averaging. And then, GU, you asked a question about why can a barrier not be adiabatic and permeable? When you have, if a molecule moves across a barrier, it inherently brings with it energy. And that means you had energy move across the barrier. So the barrier cannot be adiabatic because it allowed energy to move across it. Okay. And one other question that is a good question, and I understand why you ask it. Amana asked, if you're given a molecular formula, can you determine how many isomers exist? And the answer is, I don't know of any way. You just have to draw them. Sorry. Um, so as far as I know, there's no general formula that says if you have this many carbons, you have this many isomers. Because there's you have to then specify, is it alkane, alkene, alkyne? There's a whole bunch of other stuff you have to specify. So generally speaking, you just have to draw them and hope you got everybody. Um, but I can check that real quick for you guys. Don't forget to check in. It's actually past time. Um, nope, I Googled it. No simple formula. The number of isomers grows exponentially for higher carbon counts. So a lot. And the more carbons you get, the more possibilities. So in the end, you just have to draw it. I'm sorry. And hope that you guessed all of them. Um, Now there are ways of determining did you draw as many as you could possibly draw. And that's something to either ask for a podcast on or ask it during office hours Q&A tomorrow, and I'll walk you through that. Okay? So all of these questions I went through even though we weren't on break because all of these questions directly related, except for the last one, to the idea of open closed and heat and energy flow. So they were good ways to show that you were thinking about it, and they were good questions, but also good ways to reiterate some of these concepts. Because this is not easy. Now, we are about to go on break so that you can ask some more questions if you choose to do so. So remember, when asking questions, don't put them under the boundary. So don't reply to the announcement. Just post a question in the Q&A channel. So don't do a reply to the week 3 question boundary. That's just a boundary for me to mark week 3. Instead, apply to the posting channel for your questions. Otherwise, I might miss a question. So do we have questions? Is everybody getting the sound okay? Because I'm using a new headset and I just want to make sure the sound's coming through. So I do want to remind you that one of the things I posted in the general channel was that you should go through um, and become familiar with all of the teams. Um, I don't remember if I did it for you guys, but I spent 30 minutes in Gen Chem 1 of the last lecture literally going through every spot in Teams and showing what it looked like on the phone as well as the Teams. But I also vaguely remembered I did that for you guys. So that means that if you are not navigating Teams, still can't find where the lecture link is, still can't find where the homework and the readings and all of that is, then that's on you. You need to go back and watch that lecture. And you need to follow along with your phone or your iPad or on the computer and get where you can navigate. Now, I will remind you that we are in Module 1, not Module 0, because we are now on thermodynamics. And I will also remind you that the next homework that is due will be using the guided inquiry workbook that you are supposed to have. So if you have not received that workbook, since that homework will be due next week, if you have not received that workbook, you need to chat me privately so that I can send you those particular workbook files. Otherwise, you will not have what you need to do your homework. So, general announcements. And seeing no questions popping up, I'm going to flip this back over to start lecture. Okay. So, that is the first stage. Now, the next thing we have to do is when discussing the thermodynamic energy, I'll put a barrier. So now we have that the energy of the universe is, the change in energy of the universe is zero because the energy of the universe is constant. And we've also now divided the energy of the universe into the energy of the system plus the energy of everything else, the surroundings. And that means that the change in energy of the surroundings is equal to the negative, the change in energy of the system. And I'm reminding you that in terms of my notation, I am going to drop the subscript on the energy for the system. So if you see a subscript S, it means surroundings. If you see a subscript U, it means universe. So this is universe. Okie dokie. The reason why I just went through that is now we are going to divide the energy of the system and how that energy changes into change related to work and change related to heat. So this is heat, this is work, and this is change in energy of the system. Now, this is usually the way you will see the first law written. I gave you the first law in a much more general way because I wanted you to have the better idea of the first law that did not require a did not require the splitting it up into heat and work, because that's an arbitrary split. So the way I gave you the first law is a more general first law that's basically more of an axiom than a law, but allows us to build everything on it in a way that should make a little bit more sense. So now we're going to divide the energy of the system into work and heat. So our system can do work or it can do heat when it undergoes a change, or it can do both. Now, you'll notice here the way I've got this drawn, I've got a D here and I've got a D with a line here. And this is going to lead to a discussion that is a little bit hard to understand because you haven't had calculus yet. But we're going to do what we can do. So another way to write this that's a little bit less calculus is delta E, which is the energy wherever I end up, E2 minus E1, which I could have also written E final, the energy of the final, minus the energy of the initial, is equal to work. The work it took me to go from the initial place to the final place, plus the heat that I generated or lost as I went from the initial place to the final place. Now, this initial final we call states. So initial state, final state. And yes, when we talk about entropy, because since somebody's already asked about microstates, these states are quantum mechanical. But in how we build this up is you have the quantum mechanics of a single atom or molecule that then, because we have a collection of atoms or molecules in our box or whatever we're measuring that is large, all of those quantum mechanical states for the single one, you now have to account for all the quantum mechanical states of all of the atoms and molecules in your box. So that becomes a statistical problem, a large statistical problem. And then when you average over the box, that's when you get to thermodynamics. So microstates are directly related to entropy. Yes, that is in fact how you spread that energy out. So it's a quantum mechanical spreading of energy out. But from a macroscopic level, we're looking at averages of a whole bunch of microscopic states. But at the macroscopic level, it's work 1, 2, not work 1 plus 2. It's work 1, 2. Work sub 1, 2. We're going to explain why in just a minute. So, what's a state? So, a state for a chemical system is defined by a pressure, volume, temperature, and quantity of material. And when you define it this way, you have to know 3 of the 4 in order. So 3 of these can be changed independently. Oh my God, 3 independent variables. Ah! So sometimes we will define the state. So this is one way. Another way to define the state is pressure, density, and temperature. And in this way, you have 2 can be changed independently. And that's because you've linked density links the other 2. Now, you can only use this method for defining a state in pure systems. You can use this way for all systems. So method 1 works for everything, including mixtures. Method 2 really only works for pure, so non-mixtures. And that's because in mixtures, as you begin to change temperature or pressure, you can begin to get phase separation. You can begin to get things that come out of solution. And those things that come out of solution may do so at different temperature pressure regimes. So for mixtures, it is better to define it as pressure, volume, temperature, and quantity of material, because then you can look at each quantity of material differently for each thing. For pure systems, you only have one material, and so there you can look at pressure, density, and temperature. So basically, a thermodynamic state is defined by things you can measure in the lab: pressure, volume, temperature, or control, and quantity of material, the amount of material you have. So that's what a state is. And that means if you are changing states, you are changing one of these variables. So if I'm changing a state, I'm either changing the pressure, changing the density, I'm changing the temperature, I'm changing the volume, but I am making a physical change to the system. And that physical change results in a change of state. So I started at one pressure, say 1 bar, and I either decreased the volume or increased the amount of material, and I'm now at 2 bar. Or I changed the temperature. I can do it that way too. I increase the temperature. So now I'm at 2 bar. That's a change in state. But which one of these, so for example, if I do this pressure increase, so let's look at an example here. So if I change the pressure of a system from 1 bar to 2 bar, okay? So now, if I do this by hold quantity fixed, hold temperature fixed, then I'm holding two things fixed, and I changed pressure, so that means I had to do what? And if I'm holding these two fixed, this implies volume changed. In order to change the pressure, I had to change the volume. Now, the way I would describe this change in writing, sorry, so the way I would describe this change in writing is a closed system undergoes an isothermal change from 1 bar to 2 bar. And I would actually not call that a change. I would call this a compression. Now, closed system here implies no mass change. Isothermal implies constant temperature. One bar to two bar, this indicates the pressure change. And this compression, that's indicating the volume change. That's a pressure unit. So 1 bar is a pressure, 2 bars a pressure. This is 114. If you do not remember your pressure units, that you will need to go back and review on your own. Okay. So that simple sentence tells me a huge amount. Now I could, so that's one way I could do the change. Another way I could do the same pressure change is I could hold quantity fixed. I could hold volume fixed. And this inherently implies that temperature had to change. And I would state that as a closed system is heated under isochoric conditions from a pressure of 1 bar to 2 bar. Okay, again, this is how I would say what I just wrote in words. So, closed again, same thing, no mass change. Isochoric means constant volume. And heated means temperature increase, assuming no phase transition. And if there was a phase transition, I'd have to put it there. So that's one way. I could hold volume and temperature fixed, and that instantly implies I'm increasing quantity of substance. which means I'm adding material into the system. That you would write in words. A problem would write in words. An open system is heated. Wait, no. Undergoes an isothermal change in pressure from 1 bar to 2 bar. So that's another way of writing that. And of course, I could let all of them change. And I could just say, an open system undergoes a change of pressure from 1 to 2 bars. The truth is this one, we can only get minimal info from as a statement. So if that's all I know, I'm not going to be able to do much with it. So you're going to have to provide me some more information. You're going to have to tell me what volume did I start with, what volume did I end with, what temperature did I start with, what temperature did I end with, what amount of material did I start with, what amount of material did I end with. If all you give me is it's an open system and underwent a change of pressure from 1 to 2 bars, I can't do anything with it. I've got to know the volume, I've got to know the temperature, I've got to know the amount of material at the beginning and at the end, which of course all can be measured. Now, as long as I know that information, I can get the energy. And that's because energy, the energy of the system, this is really important, the energy of a system is a state function. And that implies only depends on the state variables. Pressure, temperature, amount of material, volume. That's all it depends on. So if I have a system and it's sitting there at a particular pressure, temperature, volume, and then I know the amount of material, I can calculate its energy. And that means, and that's the reason why I can write delta E is E final minus E initial. Because the energy of the system depends on the final state. For the final state, only depends. So this energy final is the energy at pressure final, volume final, final temperature, final amount of material. This energy initial is the energy at the initial pressure, initial volume, initial temperature, and initial number of moles of gas. As long as I know that, I can calculate it. Now, am I going to have you calculate that for a real system? Nope. Why? Very complicated, because that energy is coming from a statistical average of a quantum mechanical microstates. So it goes all the way back, but it can be done, and that's the point. Now, this is very different from what I wrote when we just started this little discussion. So what I wrote when we first started this discussion was the change in energy, which was E final minus E initial, is equal to heat 1, 2 plus work 1, 2. Addition is commutative, so I can write it work 1, 2 plus heat 1, 2, or heat 1, 2 plus work 1, 2. It's the same thing because addition commutes. 2 plus 3 equals 3 plus 2, in other words. So I can write this way, or I can write it this way. Doesn't matter. Why this sub 1, 2? Heat and work are not state functions. They depend on how the change was done. In other words, I can make the change where I get more heat, less work, or I can make the change where I get more work, less heat, or I can make the change where I get equal heat and work. But what I can't do is I can even make the change where it's all heat, no work, or all work and no heat, theoretically, on the all work, no heat. But generally speaking, the energy for all of those changes would be the same. What's differing is how I divide that energy into work and heat. So the energy, it only depends on where I start and where I end. So basically, if I were to draw this, and we're gonna go back up to what we just wrote down and show this, but quantitatively. But if I were to draw this energy and state, so here's state 1. Here is state 2. The change in energy is that. But it doesn't tell me how I got here. I could have gotten here this way, or I could have gotten there this way. You see? So the energy is not going to tell me how I made the change. It's just going to tell me how the system handled the change in terms of its energetics. Did the energy go down? Did the energy go up? But it's not going to tell me how that change was affected. What did I do to change the system? All it's going to say is, well, the energy of the system changed. How? I don't know. So if you are going to define how, you need to know how you got from point A to point B. And that was what all those words were up there, was telling you how I got from point A to point B. So let's make this quantitative after a break. Then we're going to quantitatively work on this. Okay, so questions? Of course, all of this is going to be on a test. This is thermodynamics. So yes, this is going to be on a test. We're still on the same problem. So what we're doing right now is discussing a change from a pressure of 1 bar to 2 bar. But I got to also equally discuss this as a change in volume or a change in temperature. But pressure is a good starting point as a change. But yes, this is going to be on a test. It can be both on a multiple choice test. It makes great multiple choice questions. Can be on a quantitative or qualitative test. Good question, Dylan. And yes, there is a term for. Dylan asked, what's the term for fixed pressure? Because obviously, for this particular problem, we're not at fixed pressure. It's called isobaric. Isobaric. I'm going to go ahead and write that on the whiteboard. Um, so we're not doing an isobaric change, but just so you have it, isobaric implies constant pressure. We don't really have a word for um, constant mass, because that's the difference between a closed and an open system. So technically, the very first thing your thermodynamic problem should say is if you are in a closed system, or assuming a closed system, or assuming an isolated system. In both of those instances, you've got, the mass is not changing. Now, isochoric means volume stays constant. Yes. So if all I tell you is isochoric, it means temperature could change, pressure could change. So I'm going to have to tell you something else about the system. If it's a closed system undergoing an isochoric change, then the only thing then I must have heat flow in order to increase the pressure. Um, and we're going to talk about that in just a minute. So, but that's a good question. That's What you really should begin, if you really want to get a good feel, and these type questions, post them in the question and answers part of the team, not in the general group chat, because then you get credit for it in the question and answers. So either post it in the YouTube chat or post it in the question and answers channel in Teams, but don't post it in the group chat that's part of the chat of Teams, because if you do it there, you don't get points for it. But generally speaking, one of the things you should do after this lecture is sit down and say, okay, if I have an open system undergoing this type of change, what does that lock? What can change? What cannot change? Because that'll really mean you're beginning to understand what variables you have. Okay? So let's talk about that. So let's go back up to our first one. So we're in a closed system, isothermal change. Now, before we can really do this, we need to talk about um, a couple of terms. So we need to talk about work, heat, and also energy. Now, work, that we have a wonderful, beautiful physics definition for. Sorry, camera's there. So on my old system, the camera was over there. So for work, by physics, we have force, which is a vector. Uh, we have a distance, which is an arc length, and work is let me, distance is usually symbolized by an S, and work is force dotted into a change in that positioning, that place. So work is force into a change in place. And then I have to integrate that from location 1 to location 2, and that gives me that work. So you'll normally see it written as D work is force dotted into a position. Now, the problem with this is force is a vector. It's got direction. So I will remind you, vectors have direction and magnitude. And that causes a problem between chemistry and physics. So in chemistry, we are going to be system focused. In physics, they tend to be surroundings focused. And this changes the sign of work and heat. So if we are system focused, then heat flowing out of a system versus heat flowing into a system, if we're looking from the system's perspective, That's going to have the exact opposite sign than if we were looking from the surroundings perspective. And that means that chemistry definitions and physics definitions are usually the opposite sign because of the difference between looking from a system perspective and looking from a surroundings perspective. So when I put the minus sign here for work, this is chemistry. You will not see that minus sign in physics. And that's because we are going to be looking at this from the perspective of the system. Now, there are a ton of different ways to do work, even in chemistry. There's chemical work, there's mechanical work, there's surface area work. But the two most dominant forms of work in chemistry are chemical work and expansion compression work. So for chemistry, the two we will focus on are expansion compression work and chemical work. Now, chemical work is really hard to separate from heat. So I'm going to put it under work for now, but keep in mind when you're doing chemical reactions, they also tend to generate heat or use heat. So there's chemical work / heat, because if I'm only dividing my energy, change in energy into work and heat, chemical can kind of do both, but we put it in a single term. So expansion compression work, pressure so external pressure is force per area. And this would be an external force per unit area. Rearranging this gives me external force is pressure, external pressure times area. If I plug that into this equation, I get that work is minus external pressure area ds. So this is area. These two together are a change in volume. And notice I was able to get rid of the vector because I said it was external pressure. So it's the pressure of the surroundings pushing on the system. The negative sign there is because I'm the system looking at that. So the negative sign gives me the direction. So that means now I have minus P external dV. So that's what work is. For expansion compression, I can also write this as work 1, 2 is the integral minus from volume 1 to volume 2 of P external dV. Now, written that way, we're going to come back to that. Just so you have it in your notes at this point, chemical work is defined, and we're going to come back to this next chapter. mu dN, where this mu is called chemical potential, and dN is quantity. Now, if I'm in a single phase, I have one of those terms. If I'm in a closed system that's composed of a single type of molecule, so a pure fluid, pure, in multiple phases, I would have two of those. I'd have one for liquid, one for gas, or one for liquid, one for solid, and so forth. So I'd have one set for each phase. If I'm in a mixture, I have multiple of those for phase and component of the mixture. So the number of chemical potentials I have is directly related to the number of phases I have in the system and the number of chemicals I have in the system. That's why when we get to the next chapter, we're going to have more than one term for that work. That thing can expand, in other words. But it's going to take that form. And the signs are going to be related to, is it a reactant or a product, and a whole bunch of other stuff. But it's going to take that form. I'm putting that there so it's not a surprise when it reappears, but for right now, under the assumption of a closed system, so for a closed system not undergoing a phase transition, dN equals 0. Now, for a closed system, dN, generally speaking, when we're talking about this, that's a very good question, Dylan. Generally speaking, when we're talking about this, we use the number of particles, not the number of moles. Why? It goes back to quantum mechanics, because you build from a single particle and then you build up. So generally, you start with the number of particles. But yes, I could write this as, and it's very, you will see it written this way, mu d lowercase n, which would be the number of moles. Just by habit, I wrote it with a capital N, which is the number of particles, not the number of moles. It can be written either way. But in a closed system not undergoing phase transition, dN is equal to 0. Technically speaking, in a closed system, dN is equal to 0. But if you have a phase transition, dN would be divided into the number of particles in the gas versus the number of particles in the liquid. But if it's still a closed system, the total change in mass is still going to be 0. So dN would still be 0. So for the rest of this first chapter in thermodynamics, we're going to be in a closed system. So that we can presume that no matter is leaving our system. So that we can kind of ignore chemical potential, at least for a little bit. So back to this. See, this gets way more complicated. We have two types of changes. The more common type of change is what's called an irreversible change. In that type of change, what I've got written here is exactly correct. Now, the external pressure on a system does not depend on the volume of the system. Okay? So the external pressure on a system does not depend on the volume of the system. And that means that P external is a constant relative to the volume. Because that V is the volume of the system, P external is the pressure of the surroundings. So in this instance, I can rewrite work as minus P external integral volume 1, volume 2, dV. That's the volume of the system. So this is minus P external volume 2 minus volume 1. Now, that's if the change is irreversible. I could also have a reversible change. This change is very unique. It is somewhat ideal, but there are instances where this happens, where you can set it up where this occurs. In this change, the external pressure equals the internal pressure throughout during all steps of the change. So the pressure of the surroundings is basically changing with the pressure of the system. And when that occurs, the work becomes this, where now the pressure, external pressure, has been replaced with the pressure of the system. Now the problem with that is the pressure of the system is dependent on volume. When does this type of thing occur? Some engines, some refrigerators slash heating systems are in an ideal refrigerator or engine, the changes are reversible. And in those instances, you have to handle the system change. So this is going to be in instances where you've got changes in pressure occurring inside the system in a multi-step process, and that system is isolated from the surroundings. So all of the changes, all of the heating, all of the cooling is all internal to the system. So from a system surrounding point of view, the system is an isolated system because you are heating, and the heating being applied is internal, so it's part of the system and so forth. So this can occur, and you can set up systems where this is the case. Now, the problem with reversible changes is now I have to know how pressure is related to volume. You guys know of two equations where that happens. So I have pressure is equal to nRT. I'm going to put this in a different color. So I have pressure is equal to nRT over volume. This is called the perfect gas. I also, you would probably have been briefly taught pressure is equal to nRT over volume minus NB minus AN squared over volume squared. This is the van der Waals gas. Now, neither one of these equations accurately models pressure of a real gas, i.e. a gas that i.e. a gas that can condense eventually to form a liquid. So one of the first equations that modeled a real gas sorry, I was going to try to put this. Let me grab this image real quick for you guys. Maybe it'll let me import it. So generally speaking, I love when I can't find where something saves. Oh, I always forget. F7. Okay. Images. Okay. So just so you have a sense of that equation that I just posted, um, that equation will model gases like argon, krypton, xenon, and it'll do so to pretty high accuracy. So it'll model up to the critical temperature pressure to within like 1%. But you can see how in this equation, rho is N divided by V. So you can see how much more complicated it takes to model real gases. Now, are you going to be required to know this one? No. You should know the perfect gas equation. That equation is in your data book, though. You should know the van der Waals equation. That equation is in your data book. Now, if I plug this into work for a closed system, because notice, if the system is not closed, N is changing and V is changing, and I can't do this integral. But for a closed system, so N is a constant, I can do the above integral. So in that case, I get work 1, 2 is minus P in R. Oh, well, let me do this. Volume 1, volume 2, T over V dV. That's as far as I can get. And the same would be true for the phase. So this is a perfect gas. For the van der Waals gas, I can get a little bit farther for one of them. For the van der Waals gas, I get work 1, 2 is minus NR. And then I get plus so I can solve the second equation. I cannot solve the first one for a van der Waals gas. This one is uh, that. Now, I can solve the second one because my equation only depends on one variable, volume. I can't solve the first one because I have two independent variables that can change, temperature and volume. I've already, because it's a closed system, I've already at least said N can't change. But this literally is as far as I can get with work unless I also specify what? Is the temperature constant or not? Now, if the temperature's changing, then I have to basically plot temperature and volume for my entire pressure change and do an integral. So, in other words, even here, I've specified a closed system, But even with that, I cannot calculate work without defining the path more rigorously. So work is an incredibly hard, complicated thing to define. I saw somebody post a question, and I'm hunting where you posted it. It popped up, but there it is. When we plug, again, Isley, please post your questions not under the announcement reply. Um, so please post them as a separate reply. When we plug the ideal gas equation into the work integral, are we explicitly assuming? You have to, yes. I am, uh, so yes. When I plug in the perfect gas equation, that's a very good question. When I plug in the perfect gas equation into work, I have already, instantly implies that I'm undergoing a reversible change. Because if the change is irreversible, it is always minus P external dV. And for the most part, you can assume that the external pressure does not depend on the volume of the system. So that means you're good, great, in that regard. So the moment you see something like a perfect gas equation or a van der Waals equation, or Lord help you if you have to do the Benedict-Webb-Rubin equation, which is this thing up here, the moment you have to do any of these, you are doing a reversible change. And that means you have to know how the fluid in your system is behaving functionally. Is it okay to use a perfect gas? Or do you need to use a van der Waals gas? Or are you at a temperature, pressure, volume where you have to use a more complicated equation like a Benedict-Webb-Rubin? All of that's going to depend upon where you are thermodynamically in your actual system. So that's something we will talk about of, how do you kind of judge relative for a system, where are you at? If you are in a liquid, you cannot use a perfect gas equation to model a liquid. You actually can use a Benedict-Webb-Rubin equation to model a liquid. It works for liquids. So the Benedict-Webb-Rubin equation works for liquids, works for gases, does not work for the two-phase region where you have both a gas and a liquid. So you have to be either in complete liquid or complete gas. No, it actually works in the two-phase region too. I'm wrong about that. So the Benedict-Webb-Rubin equation was one of the first equations that works across the entire phase diagram for modeling things like pressure and hence energy, and that you can use to get work in entropy. Today's modern equation of state, the one that's used by the National Institute of Standards and Technology for modeling fluids, uh, when we're talking about a system where we might undergo phase changes, but it's gas liquid, we just call it a fluid. So if you hear me say fluid, it implies I'm not a solid, but the system is either a gas or a liquid depending upon temperature, pressure, volume. So what fluid implies in thermodynamics is random motion. The particles in the system are under random motion. That's the case, you're in the fluid state. The particles in the system aren't under random motion, it's a solid. And those have statistical differences, and because of that, they have differences in entropy, and they also have differences in thermodynamic properties because of random motion. So fluids are truly are thermodynamically different from solids from a truly theoretical fundamental perspective. Okay, so I'm going to finish this off quickly. Now I have to make one more assumption to get a work that I can use for this reversible system. And that is, I'm now going to assume, I could either assume isothermal. If I do that, then work 1, 2 would be minus nRT log V2 over V1. This is for a perfect gas. If it's a van der Waals gas, I'd have minus nRT log. This is a van der Waals. So this is an isothermal reversible change. And in comparison, I'm going to put this down here where you have it for comparison purposes. And I am going to put it in a different color, isothermal irreversible change, which ironically doesn't matter if it's isothermal or not, is because that equation doesn't depend on temperature. So here, isothermal does not matter because it doesn't depend on temperature. So you can see how just changing the words, the conditions, changes the work that happens. Now, no matter what, I want this stated while we're talking about work. Work for an isochoric change. This is constant volume. You can see it in all of those equations, but you can also just go back to d work is minus P external dV. Isochoric means dV. So constant volume implies dV equals 0. So no change in volume means no work. And I don't care what type of change you're doing. Reversible, irreversible, closed, open, isolated. I don't care what your system is, what's going on. If the volume is not changing, there is no expansion, contraction work. Now, that doesn't mean that there couldn't be chemical work. That doesn't mean that there couldn't be work due to changes in surface area or length of a bar. But in terms of volume work, compression, expansion of a volume, there's no work. That's a standard trick question. The other standard trick question is that you see is what is the work for expansion? And this, by the way, gets people in trouble in terms of the universe for expansion against a vacuum. Well, vacuum implies P external equals 0. So again, dW equals minus P external, dV equals 0. The universe is not doing work as it expands. And that is the reason why when we talk about the expansion of the universe and the energy, we're only looking at, that's why the universe is cooling. That's why we're looking at a temperature only, a heat only. His work is 0. So, and energy is constant. So that's, where's things changing? What's going on? Well, that's where heat and temperature come from. So we will talk about that. But the expansion against a vacuum, again, no work. So these are all, when you're looking at this, where should you go to? You should always start for the irreversible equation, this bottommost equation, dW equals minus P external dV. This equation is true no matter what. Now, if I have no change in volume, well, dV is 0. If I'm expanding across a vacuum, P external is 0, then there's no work. Then, after I've made that decision, then I can begin to ask questions like, is the change irreversible or reversible? If it's irreversible, that's the equation I start with, and I end up, when I integrate it, with the minus P external V final minus V initial. If the change is reversible, then I have to know how the system is behaving to know what equation of state I can use to model the fluid that's in the system, and that determines which work equation I use. So you always start back at that last equation I've got written. So when you are doing anything, that's the equation you start with, and then you ask, irreversible or reversible? You look through the problem and see, because the problem has to tell you that. It'll tell you that by either saying an irreversible change or expansion against a constant external pressure. That means irreversible change. If it says reversible change, then you know you're going to have to use one of those other equations. And then it's going to have to tell you reversible change of a perfect gas, reversible change of a van der Waals gas, reversible change of a real gas, and then even for a real gas, which equation do you use? So the problems, thermodynamic problems are really wordy, and it's because we have to tell you all of this stuff. But at least on work, we can calculate it. Heat's even worse. So in order to talk about heat, I'm actually going to have to first talk about energy, because generally speaking, for most systems, we calculate the energy, we calculate the work, and we subtract the work from the energy in order to get heat, because we can't calculate heat. So heat is harder than work. And that's a good place to stop for these lectures. So any questions before I end the stream? I haven't gotten a email yet for if we're going to live stream the if we're going to Zoom the seminar today. Wait, no, today's Wednesday. We don't have seminar. I haven't gotten any information about if we're going to Zoom the seminar on Monday. As soon as I get any information about that, I will let you know. But it may not get posted until Monday at 10 a.m. for a seminar that starts at 11. It's just going to depend on if they decide they're going to Zoom it, because Monday's seminar, I think, is supposed to be in person, but we are going to try to set it up where there's a Zoom link. If they send me a Zoom link, I will post it for you guys as a bonus. If not, it's still a bonus, but you have to go in person. Other questions? I suspect there will be, but you need to go think about it. So I shall talk to you guys on Monday or tomorrow. Question and answers already posted. It's in the calendar. It's also in Module 1 classwork. Again, we're going to be running that through Teams so that you can tune in and talk to me audio-wise.